folks seem to quite enjoy our salon 2 weeks ago on GPT-3, and I'm really excited to keep running this salon and bring you a bunch of exciting talks. So today we have Yaseman Bari, who's joining us from Google Brain. But I also want to take this chance to tell you about everything that is coming up. So on September 1st, we have 2 additional talks. We've got Dylan Payton of Matthias Bethge's lab at Tübingen, who will be talking about a new strategy for disentangling features in movie data with temporal sparse coding. So this is a strategy for, say, pulling out pedestrians in a video stream. Then we'll also have, joining us from Google's developers program, Andy Furlich, who wrote a book, Deep Learning Design Patterns, and will be talking to us about some of the lessons that he learned in writing that book in the appropriate ways to, and the inappropriate ways, the anti-patterns for design of deep learning algorithms and deep learning systems. And then, so we talked about that 2 weeks ago. We already had that lined up. Now I can tell you what we've got for the salon a month from now on September 15th. We're going to have Robert Nishihara, who is the co-creator of Ray and the co-founder and CEO of Anyscale, which are respectively a tool and a company oriented towards ensuring that machine learning can happen at any scale, so that we can easily move from, single node, single chip setups all the way up to distributed multi-GPU, powerhouse applications. So Ray just recently announced an integration with weights and biases, and we're excited to have Robert on to talk about that and about what RayTune can be used for. So I think some links were dropped in the chat on Zoom and on YouTube, where you can sign up for and register for those upcoming salons. But the salon that is most recently upcoming, the one that's happening right now, features Yaseman Bari of Google Brain. So Yaseman did her PhD at Berkeley, where she studied many body quantum physics systems. And I guess deciding that that problem was insufficiently difficult and under constraint, she decided to move into machine learning and work on the intersection of physics, statistical mechanics, tools from quantum physics and machine learning, where she's done a lot of really excellent work on random matrix theory, Gaussian processes, and their application to neural networks that I've found extremely inspiring in the work that I have done. So I'm really excited to hear what she has to share with us today.
Thank you, Charles, for the introduction. And let me see if I can successfully share my screen. This. So I hope everyone can see my slides. Mm-hmm. So this is joint work that I did with great collaborators at Google, Aitor, Ethan, Joshua, and Gaia Garari. The topic that I want to talk about today is kind of has 2 different maybe components to it. One is to kind of take more of a scientific view towards deep learning and kind of understand, well, we have this large class of space of models that we're dealing with, large space of hyperparameters that we choose. Can we be a bit more concrete or be able to say something about different sorts of regimes, like distinguishing different sorts of regimes depending on our choice of hyperparameters? And the hyperparameter that we're going to focus on in this talk is really is learning rate in gradient descent or in stochastic gradient descent. I won't really distinguish between those 2. So one kind of takeaway I hope to kind of give from this talk is that this sort of kind of analysis is maybe helps inform how to choose hyperparameters and figuring out what neural networks are doing in very different hyperparameter regimes. There's maybe a second aspect to it, which is that a lot of I hope to give you maybe a taste of some of the kind of scientific progress that's been made at kind of like a basic research level in deep learning recently. And a lot of that has been surrounding neural networks that are very overparameterized. So we, as you probably heard in the GPT-3 talk, we keep making neural networks bigger and bigger, and we continue to get performance gains from them. And so, a lot of the theoretical that led people to kind of think a lot about what would happen if you took kind of limiting cases of extremely large neural networks, say neural networks that were infinitely wide. And when I talk about width, I mean that imagine you have some deep neural network, it has a fixed depth to it, but each of the hidden layers has a certain number of hidden nodes in a fully connected network, or in a convolutional network, this could be the number of channels, and we just take that number to be infinite. It turns out that you can say a lot of theoretical things about this particular limit, and that's a lot of the focus in recent and kind of the past 2 years has been on studying such networks. There's kind of very cool connections between such networks, kernel Gaussian processes, and kernel methods. And kernel methods and neural networks seem like very two different approaches to machine learning, and it's interesting that there's a connection between them when you kind of think about the dynamics of neural networks in a particular regime. So I hope to give you kind of a taste of that in this talk. And I hope this is not too technical, but please jump in with questions during it if something is unclear. So kind of the setting for this talk is we want to think about gradient descent in networks that are very wide as a function of the learning rate that we choose. And let's think about like constant learning rate SGD, but oftentimes, and all of these experiments that I'll show, we also can decay the learning rate. So really I want to talk about how does the initial choice of learning rate kind of determine what kind of dynamics you get. The results I want to show you are very particular to mean squared error, so just quadratic loss. In practice, a lot of people train with cross entropy. There's kind of a back and forth now about can we get MSE models to perform as well with as cross entropy models, and I think that's an interesting kind of question by itself. This talk is focused on MSE, but we're currently extending it to other loss functions. And kind of what I want to say as a summary of what's known theoretically about what happens with deep neural networks when they're infinitely wide. So it turns out that, as I mentioned, if you do gradient descent in an infinitely wide neural network, you're essentially just doing kernel regression. So kernel kind of is like a similarity map using features that are already fixed, chosen by you. They're not kind of learned from the data. And so in this limit, there are very interesting results that I've referenced here that tell us that neural networks just behave like a kernel method with a very particular choice of kernel. There's another way of looking at it, which is that in that limit, neural networks behave like some sort of linear model. Like the thing that you train is just linear in the parameters. And this particular linear model is really just a first order Taylor expansion of the neural network about its initialization. So, when you think of kind of back to like Taylor series in math, imagine that you took your neural network function and some function f of x, it depends on the parameters theta, and you just expanded it about your initial point. You expanded this function about its initial point. So you get kind of a first order term, second order term, and so on. It turns out that all those other terms don't matter. And the neural network just behaves as if you had kept that first order linear term, linear in parameters. But what we're trying to emphasize in this paper is that this kind of relationship only holds at smaller learning rates. And in practice, if you go and train a network that's of finite width, it's not infinitely wide, you can train at much larger learning rates. And so there's a sharp distinction between what happens at small learning rates and large learning rates that I want to talk about. So very briefly, I hope this isn't too much math in one slide, but there's going to be an object that I'm going to refer to throughout this talk, which I kind of referenced before. It's a particular kernel, the neural, what I'm going to refer to as the neural tangent kernel. And I kind of want to give a sense of why it just comes about at all. So the reason it comes about, which was kind of made evident in this earlier work that I mentioned, is that if we always think about when we train neural networks, we deal with actual parameters of the neural network. So we run gradient descent, we update the parameters, but we don't really think about how is the function evolving during the course of training. It turns out that if you try to write down the evolution equation for the function that the neural network is learning during training, it's very easy. You just use chain rule, some calculus, you can get this expression that I've shown here for MSE loss. And so there's this very special object that's appearing here that I refer to as theta. And this box equation, this tells you how to compute it. Theta is this neural tangent kernel. It's a particular kind of kernel that you get from the neural network by taking the gradients of the function that the neural network represents with respect to the parameters, and taking this inner product between these two gradients for two different points, x and x prime. Taking that dot product, that gives you one entry of this kernel. And so I only touch on this because this is kind of a core part of how we're gonna, it works into the theory, and it's how we're gonna distinguish between what's a small learning rate and what's a large learning rate. But this is something that you could easily compute when you have access to the network gradients. So the question here is now, imagine you took the model that you have and you trained it at different learning rates. What kind of phenomena would you observe? Well, in practice, you probably have a lot of experience with this. If you choose a learning rate too large, training will diverge. And that's because you're just taking like the validity of your gradient descent does not hold for step sizes that are too big. You don't really match the curvature and really the kind of geometry of the loss landscape. And so that's something that we know. But can we come up with a distinction between small and large that's also that's meaningful? And it turns out that we can, and it's related to this theory of infinitely wide networks. And the way we're going to do that is using a special quantity that I'm going to refer to for the rest of the talk, which is called lambda naught. It's basically just the top eigenvalue of some matrix. The way you construct this matrix is from this object that I mentioned on the previous slide. So you can evaluate basically this similarity matrix for every pair of points in your data set. And although maybe your data set is quite large, it's like 50,000 points, but you don't actually have to evaluate it on all those points. You can just evaluate it on a small batch of data. So in our experiments, this can be just 100 points to get an estimate of what this eigenvalue is. So construct this matrix, which has elements theta sub AB on your batch of 100 training points, compute the top eigenvalue, and we're going to use this quantity to tell us whether something is small or large. And again, this ties into all of the theory that's kind of been built around infinite width networks. So once you have this number, lambda naught, that I told you is pretty cheap to compute, you just need some gradients. You evaluate it at initialization. So you just take your random network, compute these gradients from the previous slide, evaluate it on, say, your 100 data points. So it's a 100 by 100 matrix. Diagonalize it, get the top eigenvalue. 2 over lambda naught is going to be a special learning rate that distinguishes two regimes, which I'm going to refer to as lazy and catapult. The lazy regime is something that's been studied before. It's basically the regime that I mentioned when you make the network wider and wider would give you this kind of kernel regression type learning that people know about. But what's new and what we study in our paper is this other regime that we named the catapult phase because of the sort of picture. The thing that sort of happens qualitatively is that the learning rate is too large for the sort of basin in the optimization landscape that you're initially sitting in. And so when the learning rate is too large, you migrate out of that basin very rapidly at the beginning of training and you end up in some other basin. So it kind of allows you to explore a very different part of the optimization landscape than you otherwise would have if you had trained with a small learning rate and stayed very close to your initialization. Another thing we point out in the paper is that if you wanted to know what the max learning rate is, well, empirically, we found that it tends to have this simple form of C over lambda naught. So lambda naught you've already computed. C is a number that in some networks was 4 for us, and in other networks was 12. In our theory, C is exactly 4. So that's all to say that if you measured lambda naught, you would know what 2 over lambda naught is, what C over lambda naught is, and it would tell you kind of these 3 different regimes. When am I going to diverge? When will I get catapult behavior? When will I get a lazy phase?
Yes, Mon, it looks like we have a question from Mike Trainer. They're asking, is lambda naught calculated using the initial parameter values before any gradient steps have been taken? Does it matter? How much does it change?
That's a great question. So it's computed at initialization. Even though we'll be talking about, it's a fantastic question because the catapult regime is a regime in which this number will change quite a bit. But nonetheless, these kind of demarcations are just taken at initialization. They have to do kind of with the infinite width theory. Yeah. And all of the things that I'm saying are kind of, you should take it with a little bit of grain of salt. So they're like, the difference between running SGD versus full batch gradient descent, what kind of batch size, all of these effects that I'm going to show you, we kind of tested over all these different hyperparameter choices. So we think they're pretty robust. I should say that we're dealing with networks that are pretty wide. So, in practice, they don't have to be that wide. They can be, maybe hundreds of hidden units wide. In general, I would advocate if you can make your network wider, you should try it. Because that tends to not hurt performance most of the time. But the sort of distinction that I'm talking about is one in which if you don't see a sharp distinction, you should just make your network wider and you will see it because it's really coming from infinite width or large width analysis. But so let's go to what are some of the signatures of these 2 phases, like what is different about these 2. So one of the things that's different is that if you looked at how your training or your test loss evolves in these 2 different regimes, lazy versus catapult. So let's say you choose a learning rate that's smaller than eta crit and one that's falling in this other regime between eta crit and eta max. In the catapult phase, you would find that your loss actually grows very early on in training, as if it's about to diverge, but it won't actually diverge, it'll come back down. Whereas in the lazy phase, you see kind of a smooth decrease in the loss. And so that's shown here, kind of these green and red curves are basically eta values, learning rate values that put you in the catapult phase, and the blue and orange curves put you in the lazy phase. And the model on the left is sort of toyish. It's just 3 hidden layers trained on MNIST, but you see that the same thing holds up for a wide ResNet on CFAR 10. Which is a very different setting, but you kind of see the same phenomena. The other thing that is kind of a signature of the distinction between these 2 is that if you actually looked at the evolution of lambda, which is effectively like a rough measure of the curvature of the basin that you're kind of currently in, you would see 2 very different very different behaviors. So again, the green and red curves show an eta value that puts you in the catapult phase. The blue and orange curves are in the lazy phase. And what you see is that the curvature drops pretty rapidly early in training if you're in the catapult phase, whereas you just see it kind of decay a little bit if you're in the lazy phase. And it turns out as you make it wider and wider, actually in the lazy phase, your curvature won't drop at all, because you're going to actually stay in the initial basin. This is sort of the existing theoretical result that we know. But But if your learning rate is above this value, you will evolve into another basin, your curvature will change. And again, you see kind of similar phenomenology in a wide ResNet, despite the fact that that has more bells and whistles than a fully connected network. And here, a final signature that I want to mention is you kind of see that this persists throughout training. So even if you looked at the curvature, say at a certain time or at the end of training, you'd find that in the catapult phase, so this is showing, lambda as a function of the learning rate. In general, the curvatures in the catapult phase are much smaller than they are in the lazy phase. Now, this particular plot, you can kind of see what we found was particular to networks with ReLU, which we haven't quite understood why it's different. But in networks with ReLU nonlinearities, so there's the 2 over lambda naught that I mentioned at the very beginning, which is universal across all models for being the value of eta critical. Eta max, which is this black kind of vertical line here for these models, occurs at 12 over lambda naught instead of 4. So what that constant is, kind of, again, there seems to be 2 rough cases that we see between ReLU models and non-ReLU models, but it's good to know that if you just measure lambda naught, then somewhere between 2 and 12-ish over lambda naught gives you the catapult phase. Learning rates that are smaller give you the lazy phase, and you start to diverge if your learning rate is larger than that. So if I'm doing okay on time, I just want to mention maybe 2 kind of things that you may not have heard about, but I think are, for people who train neural networks all the time, it's important to try out, and maybe, just a good thing to note, which is that there are 2 different ways, actually, well, there are many different ways you can parameterize a neural network, and the one that you're often used to in that kind of exists is what I'm going to refer to as standard parameterization. So it has to do with the fact that when you choose to initialize your parameters, you usually have some units of size of the neural network hidden in there. So for instance, you might choose the weights of your neural network to be drawn from a normal distribution, but you'll scale the variance appropriately. So in this case, the width of the hidden layer that's coming in is n, and you scale the variance as 1 over n. So that's kind of crucial for training. Like I think it's pretty widespread also, but it's crucial as you kind of change the size of your hidden layer or make models deeper and so on, that these factors kind of come in the right places, because you want to make sure that you're not losing signal or not amplifying or diminishing signal as you kind of propagate a signal through a neural network at initialization. So when you first begin to optimize. So in the standard case, what we usually do is we push those dimensions into the initialization of the parameters, and then we'll just multiply the weights into whatever came from the previous layer to give us the new layer, to give us the new function. So from f to the L-1 to f to the L. I want to point out that another thing you could have done, which was done in one of the papers that I referenced earlier, is to pull out the dimensions explicitly in the parameters. So just write your neural network as parameterized as 1 over root n times the weights. And now the weights are going to be initialized as being drawn from a normal distribution with a variance that doesn't change with size. So it's just a constant here. Sigma squared W is an order 1 constant. And at initialization, these 2 are similar. They lead to slightly different gradient descent dynamics. But the nice thing about NTK parameterization is that it's kind of more resilient to changes in model size. So a lot of the things that I talked about right now, some of the equations I showed were done in this particular NTK parameterization, which, in practice, what it would mean is if you worked in this parameterization, what you would find is that your learning rates, your maximum learning rate or your critical learning rate, as you made the network wider or as you changed its size, would stay about the same in value. It stays an order 1 constant. In standard parameterization, what happens is the learning rate actually tends to vanish with width. So if you're kind of scanning over different, this is relevant if width is a hyperparameter for you in your experiments, because if you're comparing different models of different widths, of different sizes, but you're sweeping over the same learning rate range and you're working in standard parameterization, you're not testing kind of equivalent models or an equivalent range. So that's maybe just kind of a side note. You can read more about it in this paper and elsewhere in our paper too. All of the results that I'm going to show are basically robust to whatever parameterization you choose. So actually the experiments we did are done in standard parameterization, but it's just something to be aware of about how the maximum learning rate or how any learning rate in general scales with width depending on how you've chosen this parameterization. And this is just kind of not really discussing why that happens, but just hinting, kind of giving you, touching on the fact that it does happen and it's something to maybe be aware of. So I suspect I might be low on time. And if that's the case, I might jump to the end.
Yeah, I think it'd be a good idea to jump to the end so we have time for questions.
Okay, so I won't go over the kind of one of the heart of the paper, which is that we kind of not only observe these things empirically, but we can explain them theoretically with a very simple, elegant model that comes from a single hidden layer neural network. I won't talk about it. For people who are interested in dynamical systems, I'll just say as a teaser that you can basically just analyze these two coupled update equations, discrete update equations for two variables, f and lambda. They're just two scalars, and you can recover the existence of these two phases. And so here are the numerics that come from just the analysis of this two variable kind of dynamical system that you see is kind of pretty close to the empirical results I showed you for like wide ResNet and other models. Where again, there's, eta critical is computed in a particular way, and eta max also has the form C over lambda naught, where C is exactly 4 in this particular theoretical model. So this is kind of the final slide. It's we did a lot of experiments trying to understand if there was a connection between large learning rates and generalization, because that's certainly a thing that has, people have mentioned in the past, do connections between flatter minima and generalization. So one of the things we can say kind of in this paper is, well, of course, larger learning rates lead you to lower values of final curvature and therefore flatter minima in a certain sense. Across a lot of the experiments that we looked at, it tended to be the case that larger learning rates, mainly meaning in this phase, in the catapult phase that I mentioned, did better, or that is to say that like the best performing model was often in the catapult phase. But I don't want to give kind of a universal statement about that, because again, it may depend on your problem where the optimal kind of learning rate lies. I think for a lot of problems in deep learning that people work on, particularly like image classification and things like that, it may be the case that optimal learning rate kind of lies in this other regime. I didn't really talk about this, but there's kind of this ongoing debate now and investigation and research as to what's actually happening in, what does feature learning actually consist of when we talk about that in kind of neural network models. And this catapult phase, another way to frame it is that it's one where we think there's a lot of feature learning. This object that I referred to earlier, this kernel, has to do with the features that are being learned. And so if it's changing by a great amount, then you're learning a lot of features. Whereas in the lazy phase that I mentioned, we know that in the infinite width limit, you don't do any feature learning. You just have fixed kernel regression. Using a kernel you evaluated at initialization. So there's that's an ongoing kind of topic of investigation, but here are just 3 plots that kind of show 3 different experiments. starting from on the left, a very simple system on just a small number of samples where you see a huge gain in the test performance because there aren't that many samples. And then in the middle and rightmost plots, you just see wide ResNet models on CFAR 10 and CFAR 100, where the better performing models seem to fall in the Catapult phase roughly. These are also experiments where we did learning rate decay. So again, I don't know that there's like a universal statement that I want to say, but it tends to be the case across our observations that when the model, if you make the model wider and wider, it gets better. And in general, between a small and large learning rate kind of phase, large learning rate tends to be better. So I'll end there. I'll maybe just point you to the paper if you want to read more. And also for actually computing this eigenvalue, I think the neural tangents library is a very useful library from collaborators of mine at Google. And it can help with actually measuring, constructing this NTK kernel on a batch of data, measuring the eigenvalue. And so you can use it in experiments to kind of determine how to choose learning rates and how to more generally tune hyperparameters.
Great. Thanks, Yaseman. That was a really, really interesting talk. It highlighted some of the features of your work that I didn't really get from just reading the paper, which is great. One of those that I wanted to check in on is the batch norm is known to reduce the biggest eigenvalue of the loss Hessian, which says that the loss service gets a little bit less curvy. And this is thought to be maybe the way that batch norm sort of gives you the ability to give higher learning rates. Would you expect that to also reduce lambda 0 of this tangent kernel matrix? And if so, do you think that your work helps explain a little bit of the utility of batch norm?
So that's a good question. I don't think our work does at the moment. Maybe that's a direction it could be taken in. What I didn't mention, and what because I probably needed more time to explain it in detail, is that actually this lambda naught is very closely related to the top eigenvalue of the Hessian if you're using MSE loss. So actually they're exactly the same in an infinitely wide model. And the difference comes about as you back off of infinite width. And so at finite width, there's kind of like a small correction term, which in our experiments, we actually, for a lot of the things that I showed, I don't want to say necessarily all, we also measured the Hessian top eigenvalue to study that discrepancy. And they're kind of more or less the same for models of this size. But I would expect basically that because, as you noted, batch norm reduces that top eigenvalue, then lambda naught here in a batch norm network would also be smaller. What I think that, although there's no batch norm in our theory, I think that this difference between small and large learning rate, though, nonetheless seems to persist even with batch norm models, because they are some of the models that we tested, but we don't really understand why. The theory is just a very minimal model.
For sure. Great question from Tom Bishop through Zoom. So how do these investigations relate to empirical uses of warm-up and one-cycle learning rate policies that should be very effective in practice? So just for folks listening, it's actually very common not to just use a single learning rate scalar value, but to actually cause that value to go up and down throughout training, like a sawtooth pattern. So do you think that that connects to this, the presence of these different phases in learning rates?
So that's a great question also, and not one that we understand, or at least I understand. Again, this work doesn't tell us about that. As far as I know also, from talking to practitioners, I get the sense that warm-up maybe depends, the effectiveness of warm-up depends a bit on the model, as far as I have heard. So that's something that I would kind of want to look into in understanding this. But at the moment, I don't have a good understanding of what happens, how to do the warm up, how long to have it go for, what max learning rate to achieve. The context of this paper was, I mean, one could make some guesses maybe based off of this paper, but I don't, I don't know that we'd want to do that. But for this paper, another way to interpret it is not just constant learning rate SGD, but just the choice of the initial learning rate, and then you could decay even to the same value later on, or so on. But it's that initial choice that kind of determines this distinction that I was talking about.
Mm-hmm. All right, I think we only have time for one last question. So you mentioned that for overparameterized networks, they effectively behave as though they were linear in the parameters. And so you're sort of staying close by and just doing this first order Taylor expansion. So famously, I think in some of the work that you and I have both done on when neural networks optimize and when they don't, some of the most prominent work recently has been about these very overparameterized networks and proving that they are actually locally like convex, that they don't go very far, and that and that if they don't go very far, then you can prove that gradient descent converges. So are those two phenomena related? Is it the case that those proofs like from Alan Zhu at Microsoft and similar, that those only hold in the lazy regime and not like the Catapult regime?
So that's a great question. So one, I guess there are actually, so I'm not quite sure of those other papers, whether I suspect that they're studying some properties of the local geometry and not global geometry, because this is really now a statement about the global geometry, the fact that there exists other basins that are sort of far. The older results there were a series of results that were leading, basically, I think some of the ones that you were referring to, that told us overparameterized models behave like are effectively like convex optimization is what's relevant here. And this neural tangent kernel result is is consistent with that. So it's maybe a slightly different result or flavor of result, because it's not talking, maybe the way I see it is it's not talking about the geometry in a neighborhood, maybe like actually studying, like let's say you define a neighborhood you want to study and then study all the critical points in that neighborhood, but sort of talking about the effective landscape that a neural network sees as a result of our choice of initialization is effectively a convex landscape. That's kind of the way I understood that distinction. But I think you're right that there is something to be done in between here. The Catapult result kind of suggests that that there are other basins. I should say that there's there are subtleties here that I didn't mention. So this kind of result is very relevant for finite width networks because of the way the time scale. So I showed you results that show that this kind of increase in loss happens very early in training. Out of this effective model, we can get a time scale for how fast this happens, and it grows logarithmically with the width. So it's actually a diverging time scale as you make models wider and wider. In practice, we never observed that we saw that it would scale, but it scales so weakly that it's like this catapult happens within the first few steps, or first kind of 50 steps or so of gradient descent. But to make a statement about infinite width networks, I think this basin that we're talking about, strictly speaking, at infinite width, also takes like infinite time to get to. So I think it would be kind of tricky. I don't know how to tie those two together right now, I think, but those, yeah. I do think for intensive purposes, the optimization is effectively convex when you're infinitely wide, but in practice of the widths that we're talking about, this other time scale, logarithmic time scale, is very small. And so this other regime is relevant. So this work kind of points out in some ways that there's another way to take an infinite width limit, which is that you should also take time to be infinite. And that was not accessible to the previous kind of papers as far as I know.
Yeah, it's an interesting thought. All right, so that's, I think, all the time we have, because I want to squeeze in one more talk. So thank you so much for coming, Yasaman, and for sharing your work with us. I'm excited to get Google Scholar alerts when there's new papers coming out from you and your group. So yeah, excited to hear about it, and I hope the folks in the audience did as well.
Thank you, Charles. Yeah, thanks again.
All right, now give me a second, and I will set up my talk. Okay. All right. Okay. So with this talk and most of the talks that I give at these salons, I like to go back to the basic ideas in machine learning and deep learning and sort of, give them a second thought, maybe think about them a slightly different way and talk about them in a different style. So in particular, this time I am going to talk about the neural network loss and how it can be thought of as a unit test. So the view that I think makes the most sense for thinking about machine learning is that machine learning is automated programming. So when we program, what do? We produce computer programs that have some desired behavior. It doesn't really help if we just produce any old computer program. And so when humans program, when humans do it, they write code. So we reason about the desired behavior, and then we encode text files with that reasoning. When machine learning algorithms optimize models, when we automate programming with machine learning, they observe desired behavior, and then they encode parameter values to match that behavior. This is a very different process. They have the same end result, which is a computer program, whether it's resnet.py or helloworld.py, but the process by which they come about is quite different. But let's focus on the similarities first, which is we need, in both cases, to ensure that our programs have that desired behavior. So for machine learning, we use loss functions and optimization algorithms. The optimizer will write some parameters that make the loss go down. And that is the way that we try and ensure that our machine learned algorithm is behaving correctly. For human programming, we don't use loss functions. At least I don't when I'm writing Python code. We use tests of desired behavior. So humans are going to be writing text files that make the tests pass, right? Our goal is that the code that we write passes all of the tests in our testing suite. And what I think is interesting about looking at it this way is that both of these approaches are flawed. They have failure modes. Making the loss go down on the training set doesn't always give us a good algorithm. Passing our tests does not always give us good code. And I think it's revealing that they actually end up sharing some of the same flaws. And some flaws are better known in programming, in traditional human programming, and some are better known in machine learning. So the ethos that tests should drive development is encapsulated in the principle of test-driven development, which is a workflow that says, first, I decide on the behavior of a new feature for my code. Then I write tests that will only pass if that feature behaves correctly. Then I write code that passes those tests. And then I repeat this over and over again. I come up with a new feature, I write more tests, then I write more code in that order. So what does it look like to think of machine learning in that way? Well, in that case, we're actually going to be using loss-driven development instead of test-driven development. First, we decide on the behavior for a new data point, and that usually means loading the desired target, so especially in supervised learning. Then we'll write code that tests how close we are to the right behavior. And that's exactly what our loss function is when we think of our loss as a function of the parameters. It tells us how close did we get to doing the right thing. Then we update the model so that we do better on that test, right? So we use something like gradient descent or Atom or whatever optimizer it is that we're using to update the model to improve our performance on the test. And then we do that over and over again. We come up with a new behavior that we want from a new data point, and then, or a batch of data points. And then we use the loss and the optimizer once again to improve our behavior on that new test. So this connection here is clear for an idea that's maybe taken a while for machine learning to really internalize, which is the idea of out of distribution data. So the most common failure mode for test-driven development is that the testing suite that we have is just not broad enough to cover what's encountered in real life when we get into production. We tested a whole bunch of things, but we didn't test what happened when somebody uses a name that's entirely composed of emojis. So our tests they didn't cover everything. Similarly, machine learning models can fail when the training set is not broad enough to cover what is encountered once they're in production. We don't have pictures of blue stop signs in our self-driving car data set, but maybe they're out there somewhere in the world. So this is the problem of generalization to out of distribution data, and it's as unsolved for machine learning as it is for test-driven development. But I'd be interested to see if there are any ideas from test-driven development that could help us rethink how we might handle this out of distribution data problem. One problem that's actually maybe easier to understand in machine learning and maybe less common in test-driven development is the problem of overfitting. So when I first proposed this idea about what about the loss being a unit test, somebody said, well, I don't see how overfitting fits into this idea. And that's a really important thing for people to understand. So I thought about it for a while, and I came up with this example. It's important that we remember when we think about how this process would work, that computers are actually just dumb rocks that we tricked into thinking. And they follow the letter of what we ask, not the spirit. So we might think of them as being like golems, which are a famous machine from Eastern European Jewish folklore about these machines that are essentially a danger to their creators as much as they are a powerful machine. And this idea that computers are sort of dumb and pedantic also includes when we ask them to pass tests by writing programs. So if we are, when we ask a human to write code that passes tests, they look at the tests and they try to come up with a good faith effort to write a good program that passes those tests. They look at the name of what we want, print hello world or divide by 2, and they try and come up with a good program. But computers aren't going to do that. So to extend this idea, this analogy so that it covers overfitting, I imagined what might happen if programmers were being incentivized the same way our machine learning algorithms were. So imagine what might happen if programmer salaries were tied to test passing and nothing else. Doesn't matter if the website goes down, doesn't matter if all the users on the Google Play Store give us 0 stars. If we pass the tests, we get paid, right? And also, those tests were written by somebody else, and they're going to execute the tests themselves, but they're never going to read our code, right? They're just going to look, okay, did you pass the tests or not? And I think if you think about it that way, it's clear that test-driven development is not going to be enough. And to exemplify just how badly this can go wrong, I came up with this extremely cursed and unpleasant Python example. Which is, so when we write our tests, we usually say something like, okay, there's this function foo that's in my implementation file. And in my test, what I'm going to do is I'm going to give foo some argument, and then I'm going to expect that it gives a particular output. And passing the test means that the output of foo is the expected output. This is a very common style of test. So I imagine what I might write if my salary depended on passing this test and nothing else. And I came up with this implementation of foo, which I checked in PyTest does indeed pass the test on the left without doing anything sensible whatsoever. So I used a few pieces of Python dark magic. So I looked at the traceback, I did some importing of modules and getting a hold of the test foo function, and then reading its source code. And inside that source code, I looked for an assert line, right? Because the tests that are going to be run are probably going to be assert statements. And then in that assert statement, I pull out what I'm supposed to return. And then I just return that. So, whatever the test says they want, return it. But this is clearly, not what any reasonable person would want code to do. So this is an example of overfitting to the tests. I have written code that passes the test, but it does nothing else. And this is exactly what our machine learning models do when they overfit to our training data. They become good at giving the desired behavior on the training data, but terrible at everything else. So what would the solution be? Besides coming up with a better workflow than, shackling your programmers to passing tests. So if there are some tests that these programmers cannot see, but on which they'll be evaluated, then they have no choice but to examine the tests and try and actually implement the right program, a program with the behavior we actually desire. Even no matter how nefarious they are or how lazy, like this is the only option that they have. Similarly, if there are data examples that the model cannot see, but on which it is being evaluated, then the best performing algorithm will be the one that examines the pattern of the examples and selects parameters that result in the desired behavior. And this is exactly what we do when we do like when we hold out a validation set, right? When we do cross validation, we say, here are some points you've never seen before. How are you doing on this? For programming, that would mean take some tests and apply them to the code and see, okay, do you pass these tests that you've never gotten a chance to see? And this also, I think, brings some interesting insight into a phenomenon called catastrophic forgetting. So it's been known for a really long time, back since neural networks were thought of as connectionist psychology, so way back in the 80s, that they're subject to a phenomenon called catastrophic forgetting, which is that if you take a network that's been trained to, say, solve ImageNet and then train it on a task that's, say, take ImageNet images and tell me whether they're red or green, then the performance on the first task will actually plummet over time. And this will even happen if these two tasks are very close to each other. So this is represented in this figure over here. What this figure represents is on the y-axis are the performance on 3 different tasks. So let's focus on this one up here. So first we train the network on task A and it gets good at that task. Then we start training it on task B. It gets good at task B, but it starts getting worse at task C. And then we start training it on a third task, task C, and it gets even worse. And over time, it will get back to, completely random performance on the original task as it continues to learn these different things. So this is a surprising phenomenon. I think a lot of people aren't necessarily expecting it. Can we get some intuition to it by thinking about the loss as a unit test? So the important thing about unit tests is actually that they're meant to be run before each commit. This is why when we're doing test-driven development, we use continual integration. We make sure that every time somebody tries to add code to our code base, the tests get run. These prevent code regression, right? Where we lose behavior that we had previously and we wanted in a new update. So this is something that actually Francois Cholet pointed out in a recent tweet. He said that the purpose of unit tests is not really actually checking correctness now. It's to ensure that you don't get code regression, that you don't get future breakages. So this is the real import of tests. It's probably the primary utility of writing tests is when they are run with each commit. But catastrophic forgetting actually happens when we stop testing, right? When a network trained on one task is then trained to perform a new task, the original task loss is not invoked while we're training for the new task. We don't go back and say, oh, by the way, you also still need to be good at task A. And this is equivalent to no longer testing for that old desired behavior, right? So it's like turning off the tests for module A while you're writing code that is in module B and that both of them end up touching. And so it should be no surprise that we get neural network performance regression in the same way that we would get code regression in a traditional software model with test-driven development. So the central analogy here of the loss as a unit test is that we're still programming when we're doing machine learning. The optimizer is our programmer, and we are now the managers. And so instead of using tests to ensure that our programmer is doing the right thing, we use loss functions and optimizers. And but otherwise, there's a lot of connections, a lot of similarities to what happens when humans program and when they use test-driven development. So they share the same flaws and they share the same strengths. So this is an analogy I'm kind of excited about. I'm probably going to be thinking about this a good amount in the future to try and come up with new ways that this might bring new insights into different pieces about neural networks. So that's all that I have for what I'm going to talk about. But if folks have questions, we still have a few minutes before the salon is over. So pop your questions in the chat on YouTube or in the Zoom chat if you've got them.
Charles, what are you talking about next, Salon?
So I don't have a plan for the next Salon. I think we might have some outside speaker, like a full set of outside speakers next time. But I think I have some plans for the future. But I'm gonna keep them secret for it, at least for now.
Gotcha.
Right. So a question from Dimitri M in the webinar chat. If you train on all 3 tasks at once, what happens? So this is actually a good question. I don't know whether people have tried sort of basically like, summing the loss functions together and saying, okay, you need to say, be able to do all 3 of these tasks at the same time. I think what you find is that you don't necessarily get performance as bad as catastrophic forgetting, but it's still maybe not as good as a network that is just trained on one task at a time. So what I would say, I think there's an interesting article that didn't get as much attention as I thought it should have, called avoiding superposition of many models into one. So this is a way to take a single weight matrix and use it to encode the weights of multiple neural networks, right? The weight matrices of neural networks are really big, and we actually don't need all of them in order to get the network to work, right? This is something that we know from network pruning and from network compression. And so the superposition of many models into one paper said, okay, let's try and squeeze weights for multiple tasks into a single layer, into a single weight matrix, right? And that they were able to train on multiple tasks, and even like sort of train on one, then train on the other, then train on the third, and not experience catastrophic forgetting. So I would think of that as akin to sort of doing a better job of modularizing your code and saying like, okay, right now we're working on module A, and then we're working on module B, and we're making sure that we're not touching any code that's important for that module that we've already tested. And in that case, you wouldn't worry about code regression because you're only working on stuff that matters for task B, for module B. And so, yeah, so I think that's where I think, some of the most exciting recent work on avoiding catastrophic forgetting is. And I think it's interesting, actually, that it has a nice connection with this loss as a unit test and sort of programming view of what's going on here. All right. So I've got about 6 o'clock on my clock. So to close things out, I'm going to go back to the beginning real quick and say, first, if you want to catch salons that you missed or rewatch the videos from this salon, check out our YouTube channel. So search for Weights and Biases on YouTube. You can find us. We've also got lots of other things, a machine learning course, some tutorials, a podcast. And then don't forget that we've got Robert Nishihara in a month coming to talk to us about machine learning at scale. And that in just 2 weeks, we've got Andy Froelich of the Google Developers Program and Dylan Payton of Mintius Betke's lab here to talk with us about deep learning design patterns and about disentangling features in natural data with temporal sparse coding. So the links to sign up for those salons are in the chat and on the in the slides that were shared. And I hope that you click them, sign up, and that I get to hear and see you again in a couple of weeks. So take care.
Thank you, Charles. That was amazing.